In this video, we're introducing the z-score rule, which is one of the most common tools for identifying unusual observations in quantitative data. The key idea is that we want to place individual observations on a common unit-free scale. Different data sets can have different units, dollars, inches, minutes, test points. So raw distances from the mean are not always comparable. To standardize a value, we computed z-score first subtracting off the mean and then dividing by the standard deviation. Here, xi is the observation, x bar is the sample mean, and s is the sample standard deviation. The numerator measures how far the observation is from the mean, and dividing by s rescales that distance in units of standard deviation. So instead of saying this value is 10 units above the mean, we can say this value is 2 standard deviations above the mean. That makes interpretation much more meaningful and allows comparisons across different contexts. Now let's interpret what a z-score actually tells us. The sign of the z-score tells us the direction of the deviation. If the z-score is positive, the observation is above the mean. If it is negative, the observation is below the mean. A z-score of 0 means the value is exactly equal to the mean. But the real insight comes from the magnitude of the z-score. A value of z equal to 1 means the observation is 1 standard deviation above the mean. A value of z equal to -2 means it is 2 standard deviations below the mean. The larger the absolute value of z, the more unusual the observation is relative to the rest of the data. In this way, z-scores provide a natural scale for judging whether something is typical or extreme. Why do we standardize in the first place? There are several important reasons. First, standardization removes the original units. After computing z-scores, the mean becomes 0 and the standard deviation becomes 1. This creates a standardized scale that makes comparisons easier. Second, z-scores allow fair comparisons across variables measured on different scales. For example, suppose one student scores 85 on a certain college entrance exam and another scores 1,200 on the SAT. Without standardization, we can't compare those numbers directly. But if we convert both to z-scores, we can determine who performed better relative to their peer group. Finally, standardization forms the foundation for many inferential techniques, including hypothesis tests, confidence intervals, and probability calculations under the normal distribution. However, we need to be cautious. Z-scores rely on the mean and standard deviation, and both of those are sensitive to outliers. If extreme values are present, they can inflate the standard deviation. When S becomes larger, the computed z-scores become smaller in magnitude. In other words, an outlier can partially hide itself by increasing the spread. For this reason, z-scores work best when the distribution is roughly symmetric and does not contain extreme skewness or heavy tails. In highly skewed data, resistant measures like the median and IQR often provide better tools for identifying unusual observations. Now let's introduce the empirical rule, which applies to distributions that are approximately bell-shaped. For such distributions, about 68% of observations fall within 1 standard deviation of the mean, that is between x bar plus and minus 2 times s. About 95% fall within 2 standard deviations, and about 99.7% fall within 3 standard deviations. This rule provides a quick mental benchmark for determining whether an observation is unusual. If a value lies more than 3 standard deviations from the mean, it falls in the outer 0.3% of a bell-shaped distribution and may be considered a potential outlier. Let's look at example 1, female heights. We examine heights of 261 female students. The histogram shows an approximately bell-shaped distribution. The mean height is about 65.3 inches, and the standard deviation is about 3.0 inches. Because the distribution is roughly symmetric and bell-shaped, the empirical rule applies. That allows us to estimate how many observations should fall within 1, 2, and 3 standard deviations of the mean. This is a perfect setting for using z-scores and the empirical rule, because the assumptions of approximate normality are reasonable. Let's compute the interval for one standard deviation. We see that x bar minus one standard deviation gives us a height of 62.3. X bar plus one standard deviation gives us a height of 68.3. According to the empirical rule, about 68% of observations should fall in this range. In the actual data, 187 observations, about 72%, fall within this interval. That's very close to the predicted 68%, which supports the idea that the distribution is approximately bell-shaped. Now consider two standard deviations. The interval becomes 59.3 to 71.3. The empirical rule predicts about 95% of observations in this range. In the data, 248 observations, 95%, fall within this interval. Again, the prediction matches the observed percentage very closely. This consistency strengthens our confidence that the distribution behaves like a normal distribution. Finally, look at three standard deviations. The interval is 56.3 to 74.3. The empirical rule predicts about 99.7% of observations in this range. In the actual data set, 258 observations, about 99%, fall within this interval. This confirms that only a tiny fraction of observations lie far from the mean, and values beyond this range would be considered highly unusual. So what should we do when we detect an outlier? First, investigate. Check for data entry errors, incorrect units, or measurement mistakes. Many apparent outliers turn out to be simple recording issues. Second, understand the context. Some extreme values are genuine and meaningful. Rare species sightings, extreme weather events, or unusually high incomes may be central to the story the data are telling. Third, report and compare. It is often useful to analyze the data both with and without the outlier to see how much it influences conclusions. If results change dramatically, that should be acknowledged transparently. Finally, when extreme values are present and valid, consider using robust methods, such as the median, IQR, or trimmed mean. Outliers are not automatically bad. They are signals that deserve thoughtful attention and careful interpretation.